Today I have the pleasure of introducing Professor Barry O'Sullivan of the University College Cork. Barry is a professor in artificial intelligence with a rich body of work in AI, as well as I believe a strong presence in Europe in matters pertaining to artificial intelligence. Okay, so Barry, thank you very much.
Great, thank you very much, and good afternoon or evening, everybody. So hopefully you can hear me okay. I'm just going to share my screen here. That's the wrong thing to share. So, there we go. Great, so I think I have about 1 hour to talk, and then we're going to go into some questions or something like that, and we'll all be finished by 5:30. Is that right? Or sorry, 6:30 your time. So thanks everybody for attending. My name is Barry O'Sullivan. I'm a professor of AI at University College Cork, and I'm involved in an initiative called the AI on Demand platform. It's a service that the European Commission has advocated as a strategic project in AI, and so it's a platform where you can, or rather that you will be able to avail of many different types of AI service, and you'll be able to contribute to those services and contribute data and so on. So hopefully over the forthcoming years, you'll be enjoying the fruits of that a lot. And our colleagues there are very core to that initiative. So today I'm going to talk about towards the science of trustworthy AI and what that means. And I guess I don't know the backgrounds of everybody in the audience, so this will be maybe old news to some people in the audience. It might be new to some people, but hopefully everybody will get something from the discussion, and hopefully there'll be some questions at the end. So what is trustworthy AI, and what is, I suppose we'll get to answer that question in a few minutes, but I suppose first of all the question is, what is AI, and is there a sensible definition for that, and why do we care or hear so much about AI? Well, one thing is, one thing we have to be careful about in AI is that there's this famous quote from Arthur C. Clarke, which is, any sufficiently advanced technology is indistinguishable from magic, and that's very true in the context of AI. You often hear in the public domain that AI is capable of doing things that are almost magical, and that's part of the hype around AI. We need to be very, very careful about leaving hype go unchallenged. The other quote that's true about AI, I think, is what's called Amara's law, which is that we tend to overestimate the effect of a technology in the short run and underestimate the effect of it in the long run. And I think this is very true of artificial intelligence, because the term AI was first coined in 1955 when John McCarthy and Marvin Minsky and others wrote the proposal for the famous Dartmouth Conference, which took place in 1956. And so, that's whatever, 67 years ago. And actually, I think it's 67 years ago yesterday or something that the proposal was submitted. So, while we think that AI has been a tremendous, fast-moving success, and I'm not quite sure that's really true, this is a technology that's literally been around for decades. And so I think we tend to repeatedly suffer from Amara's law in AI. We tend to, every time there's a new significant advance, we tend to overestimate its impact. And while we're caught up in overestimating it, we kind of lose the longer term picture of what are the impacts or what are the consequences of it. One of the reasons we talk about AI so much these days is because of the successes of deep learning, largely due to these three individuals, or at least these three guys are largely synonymous with the great recent successes of deep learning: Yann LeCun, Geoffrey Hinton, and Yoshua Bengio. And it's interesting that these three fellows who won the ACM Turing Prize, essentially the Nobel Prize in computer science, have 1 foot in academia and 1 foot in the industrial world. So Yann obviously is a professor at NYU, as well as being at Facebook. Jeff is a professor at University of Toronto, as well as being at Google. And Yoshua Bengio is still very much based in Montreal, at the University of Montreal, and has founded Element AI. But of course, there's a long there's a long sort of a history of AI thinkers. You know, George Boole first was the inventor, in some sense, of symbolic reasoning. Alan Turing, of course, is the person who came up with the Turing test, in one sense, this sort of thought experiment. But he also came up with, you know, the concept of the modern computing machine. John McCarthy coined the phrase artificial intelligence itself. And was a major AI genius, and of course Geoffrey Hinton, I mentioned a moment ago, in the revolution that is the use of deep learning. Just by the way, it's kind of interesting that Boole, who was the father of reasoning and symbolic logic in AI, and Geoffrey, who is in some sense, the father of pattern matching and the importance of data in AI, they're actually related. George Boole is Geoffrey's great-great-grandfather. So that's kind of a fun thing to know. But we've always been interested in AI, you know, ever since Mary Shelley wrote Frankenstein. We've always been interested in sort of thinking about machines or beings that had similar capabilities to ourselves. And so, you know, the story of Frankenstein is very much a story like that, but it's also a story of, you know, what happens when we don't take responsibility of these types of technologies and advances as much as we could. And so, you know, Frankenstein's monster was essentially, you know, not treated as the sentient being that it was, and disaster ensued, as we all know. AI is interesting in the sense that the public often see it negatively. So, you know, if you look at Stanley Kubrick's 2001: A Space Odyssey, you know, the machine eventually wipes out the human beings, and we still hear this kind of narrative today when people talk about, well, will robots take our jobs and all that kind of stuff? And I think that's really overstated. You know, I think AI is you know, frankly, just another technology, just like robotics is, just like telecommunications, and just like, frankly, spreadsheets are. You know, it's like, sure, it can emulate characteristics of intelligence that's in some way, but it's still, after all, a technology. So I suppose that leads us on to the question of what is AI. And interestingly, again, just sort of speaking historically, people have been talking about sort of thinking machines for a very long time. So this is a letter, actually, that was written to George Boole's wife just after he died. And it recounts a conversation between George Boole and Charles Babbage, who met around the 1851 Great Exhibition in London. And they together spoke about thinking machines, Boole having sort of figured out how to automate the reasoning process, and Babbage having, in some sense, figured out how to build machines that could follow programs. So these kinds of ideas are quite old. But, you know, the AI is very much around the illusion of intelligence. So you know, the Turing test, the imitation game, is really talking about, well, can we fool people into thinking that something is intelligent? One of the nicest examples I know of the Turing test being passed is a chatbot called Lady Shatterley's Tinderbot. It's a chatbot that basically chats with people on Tinder. And so if you're a man and you match with Lady Shatterley's Tinderbot, it chats with you using the dialogue of Lady Shatterley from Lady Shatterley's Lover. And if you're a woman, it converses with you as the gardener, essentially. Now, what's interesting is that women see through this almost instantaneously. They see this as a chatbot, whereas something like 70% of men who've matched with Lady Shatterley's Tinderbot have actually thought that they've been engaging with an actual human being who's been flirting with them. So at least the Turing test has been passed in some sense. Not that it's particularly important, obviously. The old heady days of, I mentioned the Dartmouth conference. So back in 1955, John McCarthy and others, very, very ambitious in terms of what could be achieved. And so you can find this proposal online, and I'd really encourage you to take a look at it. So basically what they did was they put forward a proposal for a 2-month process, for a 2-month project, 10 people. And they felt that they could really make significant progress on how to automate aspects of human intelligence. So things like the ability to learn, ability to abstract, the ability to understand language. And it's really telling that the last sentence was, we think a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for one summer. Now, any of you who go to an AI conference today, you will find that the same topics that were in this proposal in 1955 are still the topics that are being discussed at almost every AI conference that we attend these days. And so, you know, of course, there's a lot of things that these fellows did not know. They didn't know about computation and tractability. They didn't understand data. So they didn't, in the sense that they didn't understand that that there was great power in large amounts of data, and that many things could be done with large amounts of data. And so one of the great advantages of deep learning is that it can fit functions to extremely high dimensional data with billions of attributes, and that many functions of intelligence, so perception tasks primarily, can actually be emulated with functions that in that scale of dimension. And so have we learned anything about AI? Of course not. Have we learned anything about intelligence? No, we haven't. But what we have done is we've been able to use the vast amounts of data that we produce and gather these days, and maybe over the last 20 years, along with the large capability of modern machines and modern servers and databases, to give the sense that we're doing something that is intelligent. And I suppose, so what is AI? Well, you know, to someone like me, and maybe for many of you in the room who study artificial intelligence, AI is it's a bag of different techniques. You know, there are techniques around, you know, the problem of learning. So how do we learn from data? How do we train machines to generalize from data? How do we understand language? Can we codify expertise and answer queries about that? Can we understand and can we see things? Ability to speak, ability to plan, ability to solve problems. And I suppose, you know, one could say that AI is the study of computer systems that perform tasks that normally require human intelligence. Now, there's lots of problems with that definition, but it's a reasonably good definition. You know, basically, an AI system is one that does something that we normally associate with someone needing to be intelligent in order to solve it. And as an academic, we think of AI as a set of techniques that enable us to build those systems. There's lots of things that we all know what machine learning is: the generalization of data to form some model. And there are three different types of models, generally speaking: classification systems, regression systems, and clustering systems. Some of these might be supervised, some of these might not be supervised. And we can think of machine learning as an inversion of programming, in a sense. Traditional programming takes data. You as an expert, you sit down, you write a program, and it produces output. In machine learning, we take the data that might have been used as input, we take examples of the output that are being produced, and then the task is to produce the program that produced the output. And in areas where we use data to do this kind of thing, so be it through data mining activities or data science activities or machine learning activities, this last description really highlights an important aspect and an important weakness of machine learning and data-driven science, which is that unless you choose the right data, you do not get the right program. So there is tremendous expertise and there's tremendous care and attention and science in the identification of appropriate data sets to use to train AI systems or to train machine learning systems or to train any data science-based system. And that is not trivial. And in many applications that we see that go wrong in the real world, that step has been poorly understood. So be it a bias application or something else. So just to give you a sense also of why things that look intelligent don't necessarily need to be intelligent. And also, I suppose the other weakness, you know, previously the weakness of AI systems here, or the vulnerability, is the ability to choose good data sets. The other vulnerability is believing that data gives understanding, or that just because an AI system performs well, that we think that it has some understanding of the world, when in fact it doesn't. So let's take, this is a very old paper. I'm not going to I'm not going to go through this paper, but just to sort of say that people have been trying to automate the process of predicting judicial decisions for a very, very long time. This is a paper from 1963, for example. What does this kind of stuff do? Well, if you look at, say, a data set about legal cases, so take the European Court of Human Rights. They publish court cases. They have a particular structure. So there are procedures, facts, circumstances, there's the law that's been used, the provision, and the topics that have been covered. And the European Court of Human Rights does us, the AI and data researcher, the great service of actually publishing the decision of the court. And so what do these things look like? Well, here's an example of what the procedure would be. So it's a whole bunch of text that explains what is at stake here. So this is the procedure that's followed by the court from lodging an application until the judgment is made. So this is a case that originated in a particular application, some country, this court under Article such and such of the Convention on the Protection of Human Rights and so on. So that's the procedure. There's another document that gives a sense of, well, what are the circumstances of the case? So there's someone here. This is the legal argument. So there's an applicant born in a particular time, in a particular place, some background about this person, and what the facts of the case that's been argued are. Then there's the arguments of the parties. So basically, both parties put in front of the court what their position is, and again, very, very large document. And then the court decides. And so, for example, the court might say, well, it holds that there is a violation of Article 6 of the Convention, for example. And so, I suppose at this point you should be thinking, well, hold on a second, this stuff looks pretty complicated. In order to really do well at this task, you need to understand the law. So that might mean, some sophisticated natural language processing system, some sophisticated logical reasoning system. Hey, before we can do any of that, we need to really have some common sense about what the world is about. So, what does it mean for someone to be born, or what does it mean for someone to live in particular places? So, when we hear particular parts of the world, we might think of, well, these are not very developed places, for example. So we have some background knowledge or some common sense about the world. So how would you build an AI system that tries to predict these cases from those documents? Well, the really naive thing you could do is you could simply look at the documents as nothing more than sets of words. And by sets of words, I mean that you don't even care how the words occur in the text. So, if the procedures document says, well, John likes to watch movies and Mary likes to watch movies too, that's a document, right? So, and what we do is we just, look at maybe the words that are in that document. So John likes to watch movies, also football games, Mary and Tuck. And the classic bag of words representation, we basically take our words, our documents, and count each of the occurrences of each word. So the first document has one occurrence of the word John. It has two occurrences of the word likes, and so on. The second document has one occurrence of the word likes. It has no occurrence of the word Mary. Now you might think, well, hold on a second, that's a really stupid way of representing a document, because I don't even care the order in which the words appear. So how could this possibly be useful for anything? And hold that thought for a second. You could build on it a little bit more, and you could say, well, actually, you know what? Maybe the order of the words does matter. And so you could use what's called an Engram representation of the documents. We have our same documents, and now we have what we do is we take sequences of size n. So a 2 gram is a sequence of size 2. So John likes to watch. These are the 2 grams in these documents, and we store the frequencies of the 2 grams. So John likes appears once, likes to appears once in this document and once in that document, and so on. Now this seems slightly less stupid than the bag of words representation, but it's still pretty naive, because it doesn't, this representation, these numerical representations of these documents, they just count the occurrences of the words. They don't understand the words. So the fact that someone does an engram for watch movies, it doesn't understand what watching movies is. It just simply knows that this phrase appears. The really surprising thing is that if you were to take this through any classic machine learning system you can download off the web, this basically can give you accuracy in excess of 85% from many tests. So, for example, if you're using classifiers to predict Article 6 outcomes, it's 80% plus. And this is using these two representations. And so we have to be very, very careful when we look at, I suppose, not only the power of AI systems, but also their reliability. So just because this thing can give us, an average of 79% accuracy predicting these cases, doesn't mean that this system is any good. It doesn't mean that the system has any understanding or insight into what it's actually done. All of the data, all of the power of the system comes from the data, and the system doesn't understand the data. And so this isn't a criticism of AI per se, but this is something that we need to bear in mind when we're making a policy decision on these outcomes, or when we're arguing that something should be done because our AI system has an 80% predicts this thing 80% accurate, which is much better than 50-50, which is what these cases normally are. So, okay, so big speed up in AI over the last 40 years. Kasparov was beaten by Deep Blue in '96. Big search engine, big search system. 2011, IBM again beat human beings on the Jeopardy system. Jeopardy seemed like a really, really big advance, because if you're not familiar with Jeopardy, basically the question that the game host presents is the answer to the question, and what the contestants need to do is formulate the question. So that really feels like it's something that requires a lot of background knowledge and a lot of understanding of language. Of course, Watson is basically a big sort of NLP system that searches the web. AlphaGo is a game of enormous sort of complexity that fell in 2016 to Deep Blue. In 2017, a much more sophisticated game again, Texas Hold'em, fell to the Liberatus system. So basically, this was a competition between an AI system and human, and really champion human Texas Hold'em players. And even if you don't understand Texas Hold'em, you know that there's some degree of bluffing involved, or some understanding of your opponent. And Liberatus, this AI system, was really capable of completely destroying these four people at this game. And the subsequent system, Pluribus, is now essentially the most powerful Texas Hold'em player on the planet that human beings just can't possibly beat. Massive advances on self-driving cars, which have obviously become significantly less cool as time has gone on. And we're at the point now where these types of technologies are all around us in every way. And of course, with all of these questions raise ethical questions. I've already raised the question of whether some of these systems really understand the world, and they don't. But also sort of fundamental ethical questions. So in the center of this chart is some screenshots of a mannequin that's made by an Italian company. And so these are IC mannequins. And so this mannequin has, in her eyes, there are cameras installed in the eyes. And what this mannequin can do is basically profile the people who are looking at the clothing on the mannequin. So profile them, predicting their age, predicting their gender, predicting their race, and also trying to predict whether somebody likes what's on the mannequin or doesn't like something that's on the mannequin. And I think people start to find that kind of stuff a little bit creepy. Of course, it is a little bit creepy. Then there are other issues. This is Sophia the robot over here from Henson Robotics. And of course, there's lots of ethical issues that are raised over here. So things like, so Sophia has citizenship in Saudi Arabia. It's largely accepted by the AI ethics community that giving AI systems legal personhood or legal standing is unethical, because individuals, the people who built these systems, should be the people who are responsible for them. The AI system should not be, in some sense, responsible for themselves, and lots of other things. Key to all of this is data, huge amounts of data around us. We've seen lots of successes, like big successes like in skin cancer detection, we were told recently that there were major advances in the use of machine learning in the fight for COVID-19, and that might be true in some sense. Some applications that we saw in COVID-19 were basically diagnostics. So using traditional, or what have become traditional, sort of classic convolutional neural network-based approaches for classifying images. Does this person have COVID-19 or not? But what was very, very interesting is that in a study of hundreds of these tools that were published, it was shown out of this, there was a study published last year of over 2,200 studies of these diagnostic tools. Essentially all of them were flawed in some way. So none of them were of any clinical use whatsoever. And that's very interesting. And the reason they were not of any clinical use whatsoever is that in some cases there were problems with how the system was built, evaluated, how the data was gathered, how the system was trained. So fundamental methodological issues. And this is something that we need to be really cognizant of when we're doing any sort of work with that is data-driven and using techniques like AI. I suppose just one other thing I want to say, I mentioned all of these fantastic systems at the beginning of this section, Deep Blue, AlphaGo, the Texas Hold'em player, Liberatus and Pluribus. And often you hear this narrative that AI is human level in some particular area. So for example, when Lee Sedol lost to AlphaGo, there was a lot of media coverage that said, well, Go has finally become has fallen to AI, that AI is now the dominant technology. But we have to really think about what that says, because Lee Sedol was a man in his late 20s, early 30s. He has a brain the same as yours and mine. And our brains consume about 20 watts of power. AlphaGo, on the other hand, is a supercomputer that was trained on about 5,500 lifetimes of Go, where in every one of those lifetimes, AlphaGo played Go at the speed of a supercomputer for the entirety of its life, 24 hours a day, 7 days a week, without ever taking a break for sleep or anything else. The amount of power and the amount of data used to train these systems is enormous. And there's Lee Sedol with his 20-watt brain, 20-something years of age, and he has a life. He's got relationships and friendships and interests outside of Go, and there he is holding his own against this absolutely enormous computer. And so we really have to think very carefully about what success in AI looks like. But that's a slightly different topic. So responsibility. For trustworthy AI, we need to deal with sort of ethical issues. And one of my favorite books on this type of topic is Weapons of Math Destruction by Cathy O'Neill. It's a really great title, really great book. We often hear about bias, and we'll talk about that later. We often hear about AI systems going wrong. So Microsoft Tay's system going wrong, this chatbot that became the sort of racist and offensive chatbot online by observing people interacting on Twitter, which is never a good idea, obviously. Other forms of bias, so algorithmic bias. This is a very simple thing. I put in cute babies into Google, and this is what I got. And indeed, these are all cute babies, but you'll notice that they're all pink. So there's a racial bias there, because obviously Google thinks that because I'm Irish and because I myself am likely to be white, it has my profile, it knows where I'm from and all this sort of stuff. So it believes that I will find these babies particularly more attractive than, say, that's little category up there on the very top of mixed race babies. It doesn't even talk about Asian babies or African babies. These are all white, right? So that's a real algorithmic bias that's there. Sometimes these biases are really difficult to get rid of. So sometimes they're not things that we can fix algorithmically. They're not things that we can fix by being more careful about our data, but they're baked into the data fundamentally. So for example, this is really superb work done by Joanna Bryson and others, where they show that that lots of human-like biases, so for example, gender biases, are baked into language. And so this might manifest itself as, female pronouns occurring close to particular kinds of roles. So, male pronouns appearing against positions, close to positions that are dominant or leadership-like or something like this. So this is a gender bias, and it's baked into language, especially languages where you have words that are gendered but apply to everybody. So for example, even saying mankind. How many times have you heard that man is the only species that murders its own kind? I think if you spend 5 seconds thinking about it, you realize that it's actually not man in general. Man, where man means the human race, it is actually males. Males are overwhelmingly responsible for the death of human beings. So there's already a gender bias in sort of how you interpret that sentence, right? So, and these things are baked into language and very difficult to overcome. Some other sort of ethical issues around facial recognition. So lots of concern about that in Europe, especially facial recognition that is unconsented. I don't think anybody has any problem with facial recognition systems where you sort of set them up yourself. For example, Face ID on your iPhone, for example, is a perfectly decent thing to use. But if the police force is actually surveilling you, that's a completely different matter. We don't like that. Also, there's other ethical issues like the access, I suppose, equitable access to AI across the world. And so this paper highlights a very nice piece of interesting research from Facebook AI, which what they do is they look at the ImageNet dataset, this very famous dataset for training image recognition systems. And what they do is because the ImageNet dataset is a set of geotagged images, there's a whole bunch of queries you can ask of it. You don't need to ask, well, what's in this image? You can also split the data by geography, for example, and we can look at we can correlate geographies with, for example, income levels, and we can ask the question, well, is AI performing as well for all geographies and for all income levels? And this paper was able to show that this certainly is not true. That while in the West, in developed economies in the West, AI systems are very, very accurate, this is not true in countries that are poorer, that are less developed, for example. And part of the reason is, as you can see in the little images on the page, that, for example, soap appears in a whole multitude of different sort of fashions in some countries, whereas in very sort of more wealthy Western countries, hand soap is often in a plastic thing with a little pump dispenser, beside the tap, for example. So and so this is an equity or a lack of equity in benefiting from AI that we do need to be concerned about. I'm going to skip over that. And of course, there's all sorts of vulnerabilities also that we can think about. So, for example, it's easy, well, in machine learning systems, one can construct what are called adversarial examples, which are examples that fool AI systems into thinking that they are something else. So a classic example was this study done with stop signs, where a commercially available self-driving car was fooled into thinking that these were 45-mile-an-hour speed limits because the signs themselves had been hacked with little pieces of colored tape, and that these colored tapes were positioned in a way that fooled this particular self-driving car, a very, very famous brand of self-driving car, into not recognizing these as stop signs. One can also manipulate images so that they're misclassified. So you can see that that's certainly not, that's a sock, that's not an Indian elephant. And that plant down there is certainly not a macaw. But the AI system is very, very confident, the image recognition system is very, very confident that these are those things because the image has been modified in some way. And of course, this can go quite far. This is a very, very famous example of, you've probably all heard about deep fakes and how we can exploit that and how data can be used to improve the performance of these things. This is a really fascinating one, where the system basically takes a video of somebody saying something. It generates a transcript of what the person said. So I love the smell of napalm. in the morning, is what the person says for some reason. And you can edit the text. So you can edit transcript and say, well, he should have said, I love the smell of French toast in the morning. And the system will re-render the video, ensuring that the person looks like he's saying the thing that you've asked him to say. Now, some of these systems are very convincing, some of them are less convincing, but over an internet connection, on a TV, it might be very, very hard to tell these sorts of things. And there's some sort of fun aspects of this. There's a company in France called CV Dazzle, which basically will help you design a hairstyle or a makeup style that will make you essentially invisible from facial detection, or to ensure that facial recognition systems can quite recognize you. I do a lot of track 2 diplomacy work, so I go to a lot of meetings where there are all sorts of interesting sort of spooky types, people from military and intelligence agencies, and you often find people are wearing some pretty wacky t-shirts, again, partly because the t-shirts themselves are adversarial examples to facial recognition systems. So just all this sort of comes down to, well, how do we make sure that we can try and deal with some of these issues when we're building AI systems for a particular application? And I've said that, there are some vulnerabilities, and these vulnerabilities can be surprising in how easy they are to exploit. Some biases are very difficult to deal with, as I've said. So how do you sort of talk about these sorts of things, and how do you figure out if the system that you're developing is a good system? And I guess this comes down to the ethics of artificial intelligence. And I suppose the first thing is, well, what does ethics mean, and who gets to decide what ethical means? And that's not an easy question to answer. There's a very famous experiment at MIT called the moral machine experiment. And so if you Google moral machine, you get this website. And basically what you do in the moral machine experiment is you're presented with scenarios that look like this. And you have to decide basically which of these scenarios you're more happy with than the other. So for example, they're all self-driving car, kind of trolley problems. And in one side, you don't do anything, you let the car just drive. So if you don't do anything, in this case, self-driving car with a sudden brake failure will continue ahead and drive through a pedestrian crossing, which will result in 1 man being killed, 2 male executives and 1 female. And on the other hand, if you do intervene, and so you get the car to go to the other side, this will result in 3 homeless people and 1 woman being killed. Now, of course, you don't make these decisions every day, fortunately, but we do, in some sense, make decisions that are quite like it. So, how many times have you been cycling your bike and you decided, well, am I going to cycle a little bit more closely to that car than that one? If you're driving a car, am I going to drive, to avoid colliding with someone who gets out of that car? I'm going to go a little bit closer to the cyclist than I used to. These are kind of trolley problems. But the interesting thing is that they do sort of present scenarios that are, that tell us revealing things about what people accept and don't accept. And so in the Nature paper that accompanies this, what they've done is they've aggregated the results of something like 500,000 interactions with the moral machine experiment. And what's really interesting is that they look, for example, at a preference for sparing particular characters. And so, we really want to save babies and friends. We really want to save boys and girls. We really want to save pregnant women. So that's pretty out there, as a standout thing that we want to preserve. On the other hand, we're happy to sacrifice cats. Interestingly, we're happy to sacrifice criminals before we sacrifice dogs. And there's all sorts of interesting rankings in between. I'm not saying that I agree with the ranking. This is the ranking that's there, right? So, and this might come, this might make you feel uncomfortable. This is just simply an aggregation of the preferences obtained by interacting with these types of scenarios. And what's interesting is that if you cluster the results by similarity, this is a dendrogram in the paper. So basically, countries that are adjacent are closer together in terms of their preference. what they identify is that there's largely three clusters. There's this green cluster, there's this blue cluster, and there's this red cluster. And in this paper, they label these Western, Southern, and Eastern. Now, Western doesn't mean US and Western Europe, because you'll find, for example, that there are, in the West, that there are countries like Qatar and Vietnam and Tunisia. So it's just a label that they've put on them. And these countries are so similar in terms of their tastes. They probably shouldn't have labeled them Western, Southern, and Eastern. I think they're not great. They're not great terms to use. But it's interesting that the countries that are geographically close together are in different categories. So interestingly, Iraq is in this cluster that's in the Western group, so quite close to Israel, for example. Whereas Iran is very much over here, alongside Pakistan, Jordan, and Palestinian territory. So that's kind of interesting, right? So it's not the geography doesn't necessarily hold. It's just done on the basis of the aggregation of respondents. And what they look at is the values of these, what these results tell you about the values of the participants. So what you find is that in these three groupings, which they call Western, Eastern, and Southern, there are very different preferences. So, for example, in this Western category that they call it, there's a considerable preference for inaction in these experiments, and there isn't a significant preference for sparing people higher status. But in the Southern category, for example, they do tend to act far more, and status is important. So is sparing females. Not so true in the Western grouping. And the Eastern grouping, you see that they really want to spare the lawful, sparing humans, sparing pedestrians. So, and I suppose there's no great conclusion to be drawn from this apart from the fact that they are very different. And so there isn't a single sort of ethical standard that we hold systems to. It's very cultural, it's very dependent, and it's very dependent on their values. And so one of the things I had the pleasure of doing for a number of years was I was vice chair of the high-level expert group on AI for the European Commission. This was a group of experts that the Commission assembled to look at some of these issues. The chair was the tall gentleman in the center with the striped tie. That's Pekka Lapita, the former president of Nokia Mobile Phones. It was a pleasure to vice chair the committee with him. And those people from all sorts of backgrounds. People came from industry, people came from civil society, and so on. However, one thing that you'll find, and I think it stands out in the group, is that everybody, there isn't very much cultural diversity or racial diversity in the group, and that was really unfortunate. We produced two documents, the Ethics Guidelines for Trustworthy AI. And so how could you possibly frame a policy around these issues, given that there's so much difference culturally? Well, in Europe, there's a thing called the Charter for Fundamental Rights, which all sets out the rights that everybody has. And so we came up with a system which has 7 key requirements. And so first of all, we say that trustworthy artificial intelligence systems must be lawful, they must be ethical, they must be robust. So what does robust mean? If you build an AI system to process bank loans, then it needs to process bank loans, and it needs to do it well and with high accuracy. And there are 7 key requirements. And these 7 key requirements are things like protecting human agency and oversight, being robust and safe, respecting people's privacy, being transparent, being accountable, being non-discriminatory, and all these sorts of things, protecting societal and environmental well-being. And these are very much based on the European value system, which is, as I say, codified in the Charter of Fundamental Rights. We didn't do this deliberately, but if you looked at our 7 key requirements through the requirements of the General Data Protection Regulation, you saw that the General Data Protection Regulation really upholds these principles, which is kind of comforting. If you're interested in this kind of thing, we have a system online called Altai, which you can get at this website, and we'd be very interested in getting your feedback on that. And you can just email me directly if you have any issues or any problems or any questions. So how does all this become a science then? So what can you do scientifically? It's all very fine to say, well, there are these principles, and there's a charter and so on. But how can we turn these things into science? And I'm just going to quickly, in the last 15, 20 minutes, sort of go through some of the kinds of things that one can do technically. So first of all, an explanation. Well, technically, there's lots of different types of explanation. Yuta Pearl, who's been working a lot on causal inference and explainability, I suppose, describes three types of three layers to the causal hierarchy. So association. So what does sneezing tell me about what disease I have, for example? Intervention. So what if I do X, what will happen? So if I intervene and I act in a certain way, what's the expected outcome going to be? So do X, Y happens. And then there's the counterfactual, which is what if I did something different? So what is it that caused that? So it's an even more sophisticated type of explanation. So was it the aspirin that stopped my headache, as opposed to intervention, which was if I take so asking the question, well, if I take aspirin, will my headache be cured? But counterfactuals are looking at, well, what caused it? So what made it happen? And what's interesting about data is that causal information is very difficult to get from data. From data, we get lots of association. So from data, we can look for correlations in the data. We can say, well, when this happens, we tend to see that happening a lot. Frequent item set mining. We often tend to find men who buy diapers also buy beer because it just happens frequently. But there's no information that the reason the guy is buying the beer is because he has a baby, or that the reason he needs diapers is because he has been drinking beer. Right? There's no causation between these two things. We just have correlation or association, and this is very important when we want to try and find more sophisticated forms of explanation, because we do really want to focus on causality, because we want to, for example, if we're looking for climate change policy, we want to know that, well, if we do that, this is going to happen, or if we don't do that, this is what happens. And of course, that's the big challenge with climate change, right? If people don't, if we can't change people's behavior, then disaster happens. But that requires that people understand the causal relationship between the things that they do and climate change, for example. So one can look at all sorts of different types of explanations. So in constraint programming, there's also the notion of conflicts. So how can you can say that, well, the reason we can't timetable this thing in this way is because, well, there's a smaller set of requirements that you've asked for, and that can't be solved either. So there's a small conflict there that tells you what you can't have. So you can look at things like, you can explain to people what preferences they can have simultaneously, or what preferences are inconsistent with each other. And so this is the notion of conflict and relaxation. Of course, the problem with explanations is that there's usually very many different ways of explaining something. So if you're explaining, if you're a travel planner and someone comes in and gives you some preferences for their next trip, and there isn't a holiday that fits, unfortunately, there can be an exponentially many way. There can be a number of explanations exponential in the number of preferences that explain the reason why, and even there can be an exponential number of minimal and incomparable explanations. And so what do you do then? Well, you can do things like, well, select representative sets of them. So how do you do that? How do you convince users that the sets of explanations are representative of a larger set? And how do you choose that set so that they are informative? Bias is a very big one. So you often hear, and I think we have to study bias very rigorously. You often hear people saying, well, we want bias-free AI. We want bias-free decision-making. And that phrase isn't good enough, really, because the question should be, well, what kind of bias do you mean? Or how do you measure bias? Certainly there are biases like statistical biases. You sample the data, in a way that wasn't representative of the data. That's obviously a bias. But there are some biases that are difficult to eliminate. We've talked about those. But also there are different metrics for measuring bias. And sometimes we can resolve some of them, but not all of them. And just to give you an example, there's a very famous system called the COMPASS system, which is for helping advising judges to make parole decisions in the United States. And there's a long-standing argument that the COMPASS system is racially biased. And what's interesting is that it's generally believed that it is racially biased, but there are sort of rigorous arguments as to why it might not be. And there are theorems, in fact, that say that it is impossible to get rid of some of the biases. And I'm just going to very briefly give you a sense of those. And so hopefully by the end, you'll, I'm not going to argue whether COMPASS is or is not biased. I'm just simply saying that there are different ways of looking at it. And we'll just take a look at what they are. So the COMPASS data sort of looks like this, essentially. So we have, so the argument that's been made about it is that it's racially biased against African Americans when you compare it to whites. So I'm breaking up the African American versus the whites data here. In the ProPublica data set that was made available, there are 3,600, 3,600 data points for African Americans. There's 2,500 for whites. Now, of course, there's already a question of why they are different, right? So that's I'm not going to go into that question, but there is a question to be asked there. And how you read these charts is basically the COMPASS system decides whether someone is in a high risk category or a low risk category. So high risk means that they're likely to reoffend. Low risk means they're likely not to reoffend. And the data set does have in it the number of people who did reoffend and who didn't reoffend. So if COMPASS said you're higher risk and you reoffended, then it guessed you right? So you were indeed higher risk. So of the 2,100 and some people who COMPASS predicted to be high risk, 1,369 of them did actually reoffend. If COMPASS thought you were lower risk, and indeed you did not reoffend, then it guessed you right. So it guessed 990 out of 1,500 of those people correct. However, it made some errors. So there's some people that COMPASS thought were lower risk, 542, and they reoffended. So these were people that had made a mistake about it. And equally, there are people that it thought were high risk, but didn't reoffend. And of course, they really did bad by those people because they were not high risk at all. And so the dials are correct. The upper left to lower right diagonal are correct decisions, and the upward diagonal are mistakes. And so the question is this African American result different from the white result? Is it different in a way that suggests that the African American side is racially biased? And more fundamentally, should we be comparing them at all? Now, in probably all of those questions, some of you have felt some discomfort. Well, why should you not be comparing them? We want this to be fair for all categories, all groups in society. Perfectly reasonable thing to want to ask. But let's get to it. So how would you measure bias? Well, first of all, you could look at, who's considered high risk? And you could look at, hold on a second. There's 3,600 African Americans in this data set, and 2,100 of them were considered to be high risk. So the system says that 6% of African Americans are higher risk. And when we do that same calculation for the whites, it seems to suggest that 35% are higher risk. So why is that? And I think people are probably uncomfortable with that difference. That hold on a second, it looks like this system thinks that Americans are at higher risk of reoffending twice as much as the whites, and that makes us feel uncomfortable. Although you could look at the data, and you could look at the following. You could say, well, okay, but did that difference play out in terms of who did reoffend? So we have in this data set, 1,901 of the African Americans did offend out of 3,615. And that was 53%. That's not very far from 60. And if you look at the whites, 966 of them were rearrested out of 24. That's 39%. Yes, that's different, but it's similar to the rate. So we do have actual data in these tables as well. The predictions are on the are across, and the actuals are on the rows. So one could argue that, well, hold on a second, while I was very uncomfortable a moment ago that there was this difference, maybe the difference is correct. Maybe these two groups, maybe they do, offend at different rates. Now, of course, there's lots of externalities to that, up to and including, of course, if you predict that more of the African American population are going to reoffend rather than the white population, then if you're the city mayor, you're going to ask your police force to go into the African American neighborhoods. And of course, where there are police, you get arrests, and where there are no police, you don't, right? So there's all sorts of statistics like that one has to worry about. But let's just ignore that for a second. Let's just look at the data. So, it looks like there's possibly a bias, but maybe the bias is real. Maybe the bias is actually, maybe this thing that we perceive as a bias is actually a real property of the data. But let's take a look at a different way of looking at it. So let's look at the false positive rate. So let's look at where it makes mistakes. So false positive here means that you thought somebody was higher risk and they were not higher risk. So of the people who, so in this data set, the false positive rate were of these, so 805 of these people were not, did not reoffend of the total number who didn't reoffend. So if you were not a reoffender, what was the fraction of the people who didn't reoffend who this system thought were reoffenders? And that's 47%. For African Americans, that's almost twice as much as it was for whites. So this looks very strong. So this looks like, so what this says is that if Compass if Compass erroneously thinks that you're higher risk, you're twice as likely to be African American than you're white. Some would argue that's pretty damning, right? That means that, hold on a second. So, the innocent African Americans are really getting a raw deal here. You're twice as likely as an innocent African American to be considered a reoffender, right? That's a big one. There's another measure of bias, which is false negative. So this is the people that you thought were not going to reoffend, but they did. So the people who didn't, so the people who reoffended here, 1,901 African Americans, 966 whites. Where did we make the mistake? Well, we made the mistake in 461 cases for the whites and 532 cases for the African Americans. So again, if we were falsely believing that someone was not a reoffender, then they were almost twice as likely to be white than African American. This is pretty damning too. As a matter of fact, it's really damning when you take it into consideration with the previous one. If you're going to be mistakenly thought to be a reoffender when you are not, that's the previous one. This is when you're mistakenly thought that you were innocent when you were not going to reoffend when in fact you were. This looks pretty bad. There's another way of looking at the data. There's another way of looking at the data, and this is, well, it says, well, hold on a second. These are two different groupings. These are two different populations. And so shouldn't we ask whether the data set, whether the system is calibrated for the differences between each grouping? And that would be asking, well, there were 1,369 people who did reoffend, and we did want to catch those. And this was out of a group of 2,174 that the system thought were going to reoffend. And so this group, so this statistic tells us whether the data sets are, whether the system is calibrated for the two different populations. And these numbers are almost the same. Okay. So, is the system biased or not? It depends. You might not like the fact that it considers African Americans just to be higher risk than whites. But you might be comforted by the fact that, hold on a second, but it looks like that the rearrest rates are consistent with that. That might sort of counteract that. You're probably very concerned about the fact that the false positive rate for African Americans is almost twice that for whites. And that the false negative rate, the flip side, is almost twice as good as it is in the white cases of African American case. You might be very concerned about those. But you might be comforted by the fact that the system looks like it's calibrated for both groups. Now, the thing is that these three different ways of measuring bias, you cannot have calibration and equal false positive and false negative rate unless there's no difference in the populations at all to begin with. And so if your objective is to eliminate these kinds of algorithmic biases, well, you simply can't. There's a theorem that says you can't. So what you have to do is you have to figure out, well, which bias do I want to eliminate? And you can focus on that one. In fact, you might even be able to focus on more than one, but you can't eliminate all of these simultaneously. So onto a different topic, I mentioned adversarial examples. So you can study this scientifically as well. So I suppose, just go back a second. So what would you do about this? Well, you might want to build learning systems where you can constrain the confusion matrices. So you can constrain the bias that you will get, and then try to construct a classifier, for example, that gives you error matrices that are as close to those as possible that you want. You could do that, right? So that's something that's really interesting to study. On the adversarial example side, we can actually formulate the construction of adversarial examples as an optimization problem, and there's lots of papers about this. And we can also, for example, take that a step further, and we can formally verify properties of neural networks. So we can verify the extent to which they're robust against adversarial attack. We can verify to what extent systems are equivalent, because that might be a useful query to have in some cases. So we can study those also. I suppose just finally, while us scientists are sort of studying these things, there is work being done at a policy level. So in Europe, there's a new AI Act. The new president of the European Commission, European Commission, Ursula von der Leyen, said that in her first 100 days of office, she wanted to legislate for AI, and she has. There's a white paper that was published. There's also a proposal for a regulation which is available. And so what are the regulators doing about these systems? Well, the current proposal is essentially that AI systems, so I emphasize systems, so not the decision tree induction algorithm, but the system that you build with these tools, the decision-making artifact that you build, that AI systems will be given one or more of these risk categories. More because there might sometimes be a system that has multiple features, and the different features might come with different risks. So what does risk mean in this new legislation? Risk means robustness risk. So does the system do what it's supposed to do? And risk also means risk to fundamental freedoms, as in the Charter of Fundamental Rights. And the Commission are advocating that there is a set of systems that are unacceptable. So mass and social scoring, banned. Mass surveillance of populations without consent for policing purposes, banned. Other systems will have a high risk categorization, and there'll be all sorts of hoops that these systems have to jump through on the regulatory and the compliance side. There'll be AI systems with certain types of transparency obligations. So basically, a chatbot will not be able to. Chatbots will be required to tell people that they're interacting with a chatbot. So that little thing that pops up on the side of a website that says, "Well, I'm Anna. Can I answer any questions?" If Anna is not a human being, then it has to say, "Well, this is a chatbot." Right? And some systems have no risk whatsoever. So there are some things that, you know, in the recent document were banned. So general purpose social scoring, any form of exploitation of children or mentally disabled, subliminal manipulation, remote biometric identification for law enforcement. This one might strike you as weird. So why would the Commission want to ban remote biometric identification for law enforcement purposes? So if you're Berlin, you're the mayor of Berlin, Mayor of Berlin might want to know, well, hold on a second, can we put up some cameras that try to watch out for that try for, you know, terrorists in our city? And by the way, here are a list of terrorists. Here are a set of photographs of the terrorists. So are any of these people in our city? Well, the ethical argument is that the impact of doing remote biometric identification to catch those 4 or 5 or 6, whatever, that small number of individuals, but the necessity to surveil everybody, including the risks of those people being so unhappy and uncomfortable with the surveillance that they change their behavior. They don't walk down certain streets, for example. That is considered that on balance, it's that the benefit does not outweigh the risks. And so therefore it is unethical to do so. Therefore it is banned. There will be other, there'll be other systems, there'll be other things that are in that act, which we won't get into because we're running out of time. So I'm going to end it there. And hopefully you've enjoyed the whistle-stop tour of Trustworthy AI and the scientific challenges and opportunities. And I'm very, very happy to answer any questions you might have. Thanks.
Thank you very much, Barry. Are there any questions?
Good. I see a hand.
I may have a question related to artificial intelligence related to the facial recognition, maybe. How can now deal with that in a period where most of people are wearing masks? Is that something that they are trying to face in, or it's something, I don't know, they never thought about it?
Well, yes, it's a very good question. So I don't work in facial recognition personally, but I know that that, you know, some of the handset providers are trying to develop facial recognition technology that can recognize you even though you're wearing a mask. So, for example, the updated version of Face ID on Apple is supposed to be able to recognize you, even though you might be wearing a COVID-19 mask. If you're on the street, of course, it becomes more difficult, but there are ways, you know, of recognizing people once you get to see their eyes or parts of the face. And I suppose in some applications, you also get to use other sensors like gait, for example, so how the person is walking. Gait is actually a very, very strong biometric. We've done some experiments recently at the lab here on gait as measured with your smartphone, and you can actually predict, you can estimate the amount of alcohol that someone has consumed by the changes in their gait pattern as measured by their mobile phone pockets. And I don't mean, you know, two bottles of wine amounts of alcohol where you're, you know, falling down, but I mean just how your body moves is actually so sensitive. So there's lots of things you can do in biometrics. If you can't tell from the face because it's occluded, there are other things you can do. I chair the advisory board to a project at Europol on fighting the production and dissemination of child sex abuse material online. And one of the things that has to be done there is to be able to identify perpetrators. And so perpetrators can be identified using very, very small biometrics like scars in the backs of hands and things like that. So biometric identification generally is something that's extremely strong and extremely well developed. Thanks.
Thank you.
Hi, thanks for the very nice presentation. My question would be about racism. I think that you showed very well that when you train models on biased data, models will be biased. My question would be, if you think that artificially removing this bias by doing this kind of calibration that you were describing can potentially even reduce the actual imbalance that there is in society on the long term, if the systems are used more and more and are the basis of many decisions.
Thank you. It's a really great question, and I suppose there's a few different ways of coming at it. One is we have to think about what the purpose of the system we're designing is, and if there is some importance to knowing something about race, or whether there is some difference in race. So, for example, if we want to make guarantees that a system is completely blind to race, then we need to put a lot of effort into ensuring that the data doesn't have any correlated features with race. So, for example, address. If address tells you something about the likelihood that someone has a particular racial background, so we have to work on that. There can be legitimate reasons why race is important. There might be, you might be building a system that needs to be, for example, sensitive to racial or cultural issues. But it really depends on what the system that you're designing is supposed to do and how you want to treat those different races. And in fact, you also have to ask the question: if I wish to be, not just about race, but if there's some feature that I want to be blind to, does that cost something in terms of the performance of the system? So, for example, it might be, I can't think of one, but you can imagine that that there might be some consequence of mixing data from different groups that then affects the quality of the data set. Now, of course, that's no excuse for example, that's no excuse for a system to be racist, for example. But one has to be careful about what the purpose of the system is and what the right data is to gather, and I suppose how you handle that data. There are lots of trying to make data, especially large amounts of data, blind to certain features is not easy. If you wanted, where I come from, if you wanted to be blind to religion, for example, there's a lot of features you would need to sort of exclude, and lots of combinations you would need to be sensitive to in order to preclude that. The address would be a very, very long one that tells you something about someone's religion. So it's a very, very challenging problem. But I think if it is true that in the application you're developing, that it is not only important because it's ethically the right thing to do, to be racially biased, that's quite challenging. But there are tools there are statistical methods you can apply to the data to make sure that the data set is as bias-free racially as possible. There's lots of tests you can apply to ensure that that's correct. But it's not an easy task to ever try to make data sets blind to particular attributes. There's often some remnants in the data of statistics, especially if you can join the data with other sources of data. I'm not sure if that really answers the question, but it's challenging. But I think one has to look at it through the lens of, like, how do you solve the problem? You have to solve the problem I suppose, informed by what is it that the system is trying to do. If the system, you have to ask the question: is the system trying to do something that is ethically appropriate? Is the data ethically appropriate to use, and all these sorts of questions? And if there's some bias, that how do you test for the bias, and then how do you eliminate the bias? These are, there are methodologies for that. In the ALTI system, the assessment list for trustworthy AI, we deal with some of these matters. So if you want to take a look there, and if there's anything more beyond that is of interest, please let me know, and I'll be happy to answer. Thanks. Just a last question. The challenge with, say, the compass system, you'll see that there was lots of different ways in which you could look at the bias, and in some cases there was a very strong argument for why the system was racially biased, and there were some other ones where, I don't think they'd ever disprove the system being racially biased, but they were sort of counter arguments as to why the system's results were possibly reasonable. And why is that? Because I suppose the measures that were being used for quantifying the presence of bias had these different features. So I think really for me, the big challenge with addressing bias in AI systems or in data science systems more generally is what measures of bias are the important ones. So is it false positive rate? Is it false negative rate? Is it calibration? Do we want, and I think we naturally, in everyday life, we deal with these conflicting biases. So for example, when we're trying to recruit people, if we're trying to overcome, say, a gender imbalance in the cohort, we might tend to, positively discriminate in some way. It's very difficult to automate that, but I think we kind of know how to do some of that in practice. Thanks.
Thank you
Very much. It's a pleasure.